Hey students, in this video we're going to talk about absolute extreme values on a closed interval. We call those values a singular version a maximum and minimum. Plural, we'll call them maxima and minima. All right, so our main idea here is that if I give you a continuous function and we draw that function on a closed interval, then the function has to have a highest point and a lowest point. So conceptually, just say we have 2 points, A, f of A, and another point, B, f of B, where the two y values are not the same. So it will look something like this. Let's see. Let's choose. We'll go with blue. I'll go with blue. All right. So say we have, and it's just out in space. It doesn't even matter where the points are. So hold on. All right. So we have this point. We'll call this point A, f of A. And just somewhere for the sake of argument, let's say B is higher. So B F of B is out here in space. So there are a couple of ways that we could get from A to B. Now, the first way is the obvious way, where we can just go straight from A to B and make a line. So in this case, we can see that A F of A, this is our minimum value. And B F of B is our maximum value. Now the line might continue. So again, we're restricting, let's put up some boundaries. So we're restricting ourselves to be somewhere between A and B. We can't go outside of that. So it's possible that our graph continues this direction and it continues in that direction. Great. So, but all this means is that strictly between A and B inclusive, um, that our minimum value occurred at our left endpoint and our maximum value occurred at our right endpoint. So that's one thing that could happen. Another graph that we could have is we'll take the same concept. We'll have this is going to be A, and we'll say this is B. And so again, for the sake of argument, let's say we put A here. So we have A, F of A here. And then we'll put our point B, F of B here. So now if we didn't go from A to B using a line, then what we could do is have like a curve that's something like a parabola or something where we could go up, but then if we go up, we have to go back down. So now what we see is that here at this point, A F of A, this is it's the smallest value that's on or between the red lines. And this point B F of B, well, it's nothing. It's not the highest value and it's not the smallest value. Our highest value occurs like here. And what we should know is that if I'm looking at this graph, then here the tangent line at that point is equal to 0. So we can say like the slope of the tangent equals 0. So all that means is that the derivative for some value is equal to 0 here. So we don't know what this point is. We'll call it CF of C. So we'll call this point CF of C. So like in these two examples of graphs, what we can see is that if I restrict a function, a continuous function, which is important, is that if I restrict a continuous function on a closed interval, then my maximum or minimum value, it could occur at the endpoints of my interval, or possibly where my derivative is 0 inside the interval. Now, the other way that we could have gone from A to B is let's use green instead. So we could have had like point A as the higher point. So we'll call this point A, and then we'll still have point B, but it's lower now. So we could have gone from A to B using a graph that does something like this. But now all that means is that we have two places where f prime of, we'll say like D equals 0 and f prime of equals 0. There are two places where we would have to check. Now, if you have the graph, it's obvious, but what we aim to do is move from graphs to just having analytical ways of solving our problems. So what we're really doing is we're checking the derivative for where it equals 0, comparing that function value in the original function to the function values of our endpoints. So in this graph that we have off to the right, and we're in the interval -2 to +4, then our absolute maximum is just the highest value. Excuse me, is the highest value between from x equals -2 to x equals 4, and we're considering the y values. So it seems like our maximum occurs here. It has a maximum value of 21 at x equals 4, then it seems like we hit our minimum value of 15 at x equals -2. Now, along the way, we can see that our derivative is 0 twice. Here we know that f prime of 2 equals 0. We also know that f prime of 0 equals 0. But neither one of the y values associated with those derivative zeros is higher than or lower than the values at the endpoint. The places where our derivative is equal to 0 is called a critical number or a critical value. We have critical values where our derivative is either 0 or undefined. So remember, the undefined part is going to come where we have a rational function and the denominator is 0. So in these examples, we want to determine the maximum and minimum. So our minimum value for graph A seems like it is a minimum value of 1 at x equals 0. And our maximum value seems to occur at x equals 2. And it's 1, 2, 3, 4, 5. So our maximum value is 5 at x equals 2. For B, we have still a minimum of 1 at x equals 0. But then we don't actually have a maximum. Because remember, what this open circle means is that we can get closer and closer to that value without ever equaling it. So no maximum. And almost similar for graph C is that we have no minimum because we get closer either direction. We get closer and closer to 1, but we don't ever actually get there. So we do have a maximum value of 5 at x equals 2. So the reason B and C don't produce both a maximum and a minimum is that those aren't closed intervals. So remember, a closed interval is going to give us filled in circles at along for everywhere. The function is defined at every possible point. So what we're saying is that B and C aren't on closed intervals. So they can't produce an absolute maximum and an absolute minimum. So what we have this thing called the extreme value theorem, and it just we'll say more mathematically says what we started at the beginning of the video, that if a function is continuous on a closed interval, it has to have a maximum value and a minimum value on that interval. It might be the endpoints, it might be where the derivative is equal to 0 interior to the interval. So the process of doing this is very straightforward. We find our critical values. They have to fall between our endpoint values, and then we evaluate the function at the endpoints and the critical numbers. The highest value is the maximum. The smallest value is the minimum. I've graphed these on Desmos ahead of time so we can see what this looks like, so our eyes can confirm what our math tells us. All right, so we have the first function we have is f of x is 3x squared minus 24x minus 1. So the first thing I would always do is just evaluate the function at its endpoints first. So f of negative 1 is equal to 3 times negative 1 squared minus 24 times negative 1 minus 1, which is 3 plus 24 minus 1, which seems like it is 26. F of 5 is going to equal 3 times, all right, so 5 squared is 25, so 3 times 25 minus 24 times 5 is 120, and minus 1, so that's 75 minus 120. That's negative 45 minus 1 is negative 46. So if we write this more organized, so we'll say at our endpoints, we get 2 points. 1 point is negative 1, positive 26. The other point is 5, negative 46. So again, we're comparing the y values of these points to find our maximum and minimum. So the next thing that we need to check is, do we have critical values somewhere inside negative 1, inside our interval negative 1 to positive 5? So that means that we need to find our derivative. So f prime of x is equal to 6x minus 24. And if we set that equal to 0, we get the equation 6x equals 24. And so if we divide both sides by 6, x equals 4. So 4 is our critical value. To find the critical point, we take that 4, substitute it back into the original function. So we'll call this our critical point. And so if we substitute in 4, let's see what we get. So f of 4 is equal to 3 times 4 squared is 16 minus 24 times 4 minus 1. So that's 48 minus 96 minus 1, which is negative 49. So it seems as if our maximum is 26 when x equals negative 1, and our minimum is negative 49 when x equals 4. So let's hop into Desmos and see if that is actually true. So when we look at our graph, so when x is 4, we get negative 49, and we can check our endpoint. So when x was 5, we got negative 46, and when x was negative 1, we were at positive 26. So visually, we confirm what we just did analytically. But the whole point of calculus is that sometimes we don't have graphs, and we have nice calculus methods for doing this stuff. So for number 2, we have the function 6x cubed minus 6x to the 4th plus 5. If you want, I recommend pausing the video, seeing if you can come up with the answer without me, and then jumping back in to see what I get. So first, let's evaluate our function at the endpoint values, I'm going to just change my color. Let's see. So f of -1 is equal to -1 cubed is -1. So we're going to get -6 minus 6 plus 5, which is -7. And then f of 2 is going to be 2 cubed is 8 times 6 is 48. So 48, 2 to the 4th is 16. So times 6 is -96. And plus 5 is -48 plus 5 is -43. All right. So now we need to see if we have critical values in this interval. So let's see. F prime of x is 18x squared minus 24x cubed. And if we set this equal to 0, all right, so the first thing we can do is factor out x squared. So that would give us x squared times, actually we can take out, 6x squared. So that would give us 3 minus 4x equals 0. So two things are true. One is that 6x squared equals 0. So x equals 0. And the other one is 3 minus 4x equals 0. So 3 equals 4x. And 3/4 equals x. So next we check our function at 0. So f of 0 is, so we'll say this is for our critical points. So f of 0 is 0 minus 0 plus 5, which equals 5. And then f of 3/4, I actually have no idea. Let's hop over into Desmos. Oh, I didn't put the right function. That should be 6x cubed and 6x to the 4th. And we need to do g of 0.75. It should give us that as a decimal if you want it. Yeah. So 71 over 128, I think 5.63 makes more sense. So that's 5.63. So our maximum value is here. This is our maximum, and the -43 obviously is our minimum. So again, if we go to Desmos, turn this graph off, turn this one on, then again, what we see is that at x equals 3/4, we get our maximum, which was 5.63, and really close behind it was what happened at 0. And then way down here, we get that value to -43. All right, so again, just visually confirming what we're doing analytically. For part C, we get into like a rational function. All right, so still, first thing I would do is evaluate the function at the endpoints. So we have f of -1 is going to be, so 3x to the 2/3, x to the 2/3 is the same as the cube root of x squared. So -1 squared is 1, and then the cube root of 1 is 1. So we're going to get 1 plus 2 plus 1, which equals 4. And then f of f of 8 is going to be the cube root. Well, 8 squared is 64. Cube root 64 is 4. So 3 times 4 is 12 minus 16 plus 1 and that equals -4 plus 1 is -3. So for our endpoints, we have the point -1, +4, and we have the point 8, -3. So right now it seems like the maximum is 4 and the minimum is -3, but we could have a place where our derivative is equal to 0. So f prime of x is equal to 2/3 times 3 is 2. We want to get 2x to the 1/3 minus, to the -1/3 minus 2. And if we set that equal to 0, what would I do if I were you? All right, so algebraically, this would be like having 2 over x to the 1/3 minus 2 equals 0. So we would get 2 over x to the 1/3 equals 2. And we multiply both sides by x to the 1/3. So we get 2 equals 2x to the 1/3. Divide both sides by 2. So 1 equals x to the 1/3. If we cube both sides, 1 cubed is going to equal x to the 1/3 cubed. And so actually we just get x equals 1. So we also need to check f of 1. And so f of 1 is going to be 3 minus 2 plus 1, which seems like we get 4 minus 2, which is 2. So our maximum value is, so this corresponds to be our maximum, and this corresponds to being our minimum. Let's go check that one. I put the intervals in wrong. That should be from -1 to 8. And let's turn this one on. We don't need that anymore. So when x was -1, we should have gotten 6. And when x was 8, we got -3. Hold on, let me check my math. May have made a silly math mistake. Oh, yeah. Excuse me, because we didn't multiply by 3 here. That should be 3 times 1 plus 2 plus 1. So, yeah, that's going to give us 6 instead. So, yeah, my bad. So, that's going to be -1, 6. So, again, Mr. Warren made a mistake. So, it should be 3 times -1 to the 2/3, which is 3 times 1 plus 2 plus 1, which is going to give us 6. All right, so last is, and we'll trust that this one is true without actually looking at the graph, even though I do have the graph. All right, so we got this trig function on the interval 0 to 2 pi. So f of 0 is the sine of 0 squared plus the cosine of 0. The sine of 0 is 0, cosine of 0 is 1, so 0 plus 1 is 1. And similar for 2 pi is the sine of 2 pi squared plus the cosine of 2 pi, which is 1 as well. So we could have critical values inside the interval. Let's see then. So f prime of x. So the derivative of sine squared is 2 times sine to the first power multiplied by the derivative of sine, which is cosine x, and the derivative of cosine x is negative sine x. So remember the chain rule. So this derivative requires the chain rule. And so we set our derivative equal to 0. So first thing we can do is factor out a sine x. So we get sine x times 2 cosine x minus 1, and that equals 0. So if sine x equals 0, what is true is that x is equal to sine inverse of 0. Now, really, we would be on the interval 0 to 2 pi. I'm sorry, incorrect. We would be on the interval from negative pi over 2 to positive pi over 2. But our interval has shifted from 0 to 2 pi. So sine is 0 at 0, at pi, and at 2 pi. Now, two of those we already checked. So now we just need to check f of pi, and that'll get us something in a moment. And so the other possibility is that 2 cosine x minus 1 is equal to 0. So which means 2 cosine x equals 1, cosine x equals 1/2, and x equals cosine inverse of 1/2. And inverse cosine is defined on the interval 0 to pi, but because our interval gives us 0 to 2 pi, we're taking two trips around, really. So one place where x is where cosine is 1/2 is at pi over 3. The other place is x equals 4. I'm sorry, not 4 pi over 3, 5 pi over 3. 300 degrees and 60 degrees. So 5 pi over 3. So that means you have to check these values. So f of pi is sine squared pi plus cosine pi, which is just -1. F of pi over 3 is equal to, all right, so the sine of pi over 3 is the square root of 3 over 2. So the square root of 3 over 2 squared plus the cosine of pi over 3 is 1/2. And so that's going to equal, so this equals 3/4 plus 1/2, which is, what's that, 2/4? So 5/8. No, Miss Mar, you crazy. That's insane. That is 3/4 plus 2/4, 5/4. Well, I was saying 5/8. 5/4. And then f of 5 pi over 3 is, all right, so the sine in this case is negative square root 3 over 2, then squared, plus the cosine of 5 pi over 3, which is still 1/2. So we end up with 5/4 again because the negative is squared. So our maximum occurs in two places. So our max is 5/4 at x equals pi over 3 and x equals 5 pi over 3. And our one minimum occurs when we had one a -1 is at f it is -1 at x equals pi. So let's go back over to Desmos to confirm this. And so here we see at pi over 3 we get 1.25, which is 5/4. Same thing at 5 pi over 3, and then at pi we get -1. At 0 we had 1, and at 2 pi we also had 1. Cool. So that is our video on maxima and minima. Again, the key rule here is that we find the critical values by setting the derivative equal to 0. We evaluate our original function at the critical values and the endpoints. The highest value is the maximum. The smallest point is the minimum. Thanks.